Hello and welcome back to the physics presentation. This is a revision program prepared exclusively for grade 12 students. In today's revision, we are going to cover the second chapter of grade 12 physics, which is about oscillations and wave. Stay tuned. As you know, students, the second unit of grade 12 physics contains two main parts. The first part is about oscillation in general and about simple harmonic motion specifically, and the second part is about wave motion. Any motion that repeats itself in a regular interval of time is called periodic motion. The uniformly rotating Earth represents a periodic motion that repeats itself every 24 hours. The motion of the Earth around the Sun is also periodic, repeating itself every 12 months. A body that undergoes periodic motion always has a stable equilibrium position. Simple harmonic motion. Simple harmonic motion, or SHM in short, is a special type of periodic motion in which an object oscillates back and forth or up and down about an equilibrium position between two extremes, such that its acceleration is always directly proportional in size but opposite in direction to the displacement. Common examples of objects that execute simple harmonic motion are simple pendulum and a spring mass system. The following are some of the important terms that we use to describe simple harmonic motion. Displacement. The displacement x of an object executing simple harmonic motion is the distance moved by it in a specific direction from the equilibrium position. Amplitude. The amplitude is the maximum displacement of the oscillating object from the equilibrium position. Period. Period is the time taken by the oscillating object to complete one full cycle. And another important term is frequency. Frequency is the number of full cycles completed by oscillating objects per unit time. The unit for measuring frequency is called Hertz, and 1 Hertz is equal to 1 cycle per second. One of the fundamental laws that govern simple harmonic motion is Hooke's law. On the relation between force and displacement, Hooke's law states that the force applied to stretch a spring is directly proportional to the displacement from equilibrium position, and the restoring force, the force which is responsible for the displaced object to go back to its original or equilibrium position, is always directly proportional to the applied force. In fact, it has the same magnitude as the applied force but in opposite direction. Mathematically, Hooke's law can be stated as force of restoring is equal to the negative of k times x, where k is called the spring or force constant measured in Newton per meter, and it measures the stiffness of the spring. On account of Newton's second law, we have the force net, or the net force acting on the object, is equal to mass times acceleration. In case of simple harmonic motion, the net force is equal to the restoring force, which is minus k times x. Solving for a, the acceleration of an object executing simple harmonic motion can be determined by the equation a is equal to minus k over m times x. And you can see that the acceleration gets maximum value whenever the displacement gets its maximum value. This equation justifies that the acceleration of a simple harmonic motion is directly proportional to the displacement but in opposite direction. The displacement time graph for an object executing simple harmonic motion is sinusoidal. A sinusoidal is an oscillating graph that can be described mathematically using a sine or cosine function, and the expression for the displacement x as a function of time can be determined with the help of this graph. The general expression for the displacement of an object executing simple harmonic motion as a function of time can be stated as x as a function of time is equal to a amplitude times cosine of omega t plus phi, where phi is called the phase angle and it represents the angular displacement at the initial condition, that is at t is equal to 0. With the help of this equation, we can also determine the expression for the velocity and acceleration of an oscillating object, which are given by the first and second derivative of the displacement. As such, the velocity of an object executing simple harmonic motion as a function of time is given by this mathematical expression: v is equal to minus omega times a times sine of omega t plus phi. And also the acceleration is given by minus omega squared times a times cosine of omega t plus phi. We can also determine the velocity of the oscillating object in terms of the displacement x from the equilibrium position as v is equal to the square root of k over m into a square minus x squared. So now let's see some practical examples on these topics. A mass of 3 kg is placed on a vertical spring and the spring stretches by 10 cm. It is then pulled down an additional 5 cm and then released. You are asked to find A. the spring constant, B. the angular frequency, omega, C. the frequency of oscillation, D. the time period, E. the maximum velocity of the vibrating mass, F. the maximum acceleration of the mass, and G. the maximum restoring force, H. the velocity of the mass at x is equal to 2 cm. Now let's try to solve these problems one by one. We know that the spring constant is found from Hooke's law as K is equal to the force applied divided by x, and we know that F is equal to the weight of the mass, which is m times g divided by x, and we know that F is equal to the weight of the mass divided by x. So the mass is 0.3 kg times gravitational acceleration, which we take 10 meters per second square for simplicity, divided by 0.1 meter, which yields K is equal to 30 Newton per meter. The angular frequency omega, also found from the expression that omega is equal to the radical of K over m, which is K 30 Newton per meter divided by 0.3 kg, which results in the square root of 100, which is equal to 10 rad per second. The frequency of motion can also be found from the expression frequency is equal to omega divided by 2 pi. We have calculated the value of omega 10 rad per second divided by 2 pi, which yields 1.59 Hz. Since we already know the frequency f, it's easier to calculate the period t, and we know that period is equal to 1 over frequency. 1 divided by 1.59 Hz gives us 0.628 seconds. The maximum velocity can be found from the expression V max is equal to A times omega. We know the amplitude is 5 times 10 to the power of minus 2 meter, that's 5 cm, times 10 rad per second, which gives us 0.5 meter per second. Also, the maximum acceleration is found from the expression A is equal to 5 times 10 to the power of minus 2 meter times 100 rad square per second square, that's omega square. Finally, the maximum acceleration will be minus 5 meter per second square. The maximum restoring force can also be determined using Hooke's law, and the maximum force is given by minus K times A. We know K is equal to 30 Newton per meter times A, which is 5 times 10 to the power of negative 2 meter. We know that K is equal to 30 Newton per meter and A is equal to 5 times 10 to the power of minus 2 meter, which yields to a maximum restoring force of 1.5 Newton. The minus sign here shows that the restoring force is always directed into the equilibrium position. The velocity of the mass at x is equal to 2 cm can also be found from the expression V is equal to plus or minus omega into a square minus x square. Is also equal to 10 rad per second into the radical of 5 times 10 to the power of minus 2 meter square minus 2 times 10 to the power of minus 2 meter square, which finally gives us a value of V which is equal to plus or minus 0.46 meter per second, where V is positive when moving to the right and negative when we are moving to the left. Damped oscillations. In real systems, simple harmonic motion is subjected to energy loss due to drag force like friction. This energy loss process is called damping, and it's characterized by decreasing of amplitude. Depending on the magnitude of the drag force, we have 3 kinds of damped oscillations. The first one is called critically damped oscillation. Critically damped oscillation is a kind of oscillation in the presence of extremely large damping force. The system no longer oscillates, but rapidly returns to its equilibrium position without oscillation when it's displaced and released. The second kind of damped oscillation is called overdamped oscillation. This is a kind of oscillation in the presence of large damping force. Again, there will be no oscillation, but the system returns to equilibrium more slowly than with critical damping. And the third kind of damped oscillation is called underdamped or light damped oscillation. This is an oscillation in the presence of small damping forces like air resistance. The system oscillates with steadily decreasing amplitude. Forced oscillation and resonance. Consider an oscillating system that when left to itself oscillates at a frequency of f0. We call this frequency the natural frequency of the oscillator. Suppose that this system is subjected to a periodic external force of frequency fd. This frequency is called the driving frequency. The amplitude of oscillation is generally not very high if fd differs from f0. As fd gets closer and closer to f0, the amplitude of oscillation rises dramatically, and this condition is called resonance. Wave motion. A wave is a continuous self-propagating disturbance that moves away from the source, carrying energy, momentum, and information from one place to another without the transport of matter. There are two general classifications of waves, mechanical and non-mechanical, or electromagnetic. Mechanical waves are waves that require material medium for propagation. They use the particles of the medium to carry and transport energy. Examples of mechanical waves are waves on strings and springs, waves on water surface, sound wave, and seismic waves. Electromagnetic waves, on the other hand, are waves that can propagate through a material medium as well as through vacuum. They are caused by oscillating magnetic and electric fields. Examples of electromagnetic waves are light, infrared wave, radio waves, X-rays, and gamma rays. When a wave propagates through a medium, the particles of the medium vibrate above their equilibrium position. On the basis of the direction of propagation, traveling waves can also be categorized as transverse and longitudinal. A transverse wave is a wave in which the particles of the medium execute simple harmonic motion in a direction perpendicular to the direction of propagation. All electromagnetic waves are transverse waves. Longitudinal waves are waves in which the particles of the medium oscillate in a simple harmonic motion parallel to the direction of the wave propagation. A typical example of a longitudinal wave is sound. During wave motion, the particles at the equilibrium position x displace some distance y perpendicular to the x-axis. So the value of y depends on the particles that we are considering and also the time at which we are looking at it. Thus, y is a function of both x and t. Therefore, the mathematical expression for a wave traveling along the x-axis is given by y as a function of x and t is equal to a times sine of kx plus or minus omega t plus phi, where a is the amplitude of the wave, k is called the wave number or propagation constant of the wave, omega is the angular frequency, and phi is the phase constant of the wave. It tells us the initial value of y at x is equal to 0 and t is equal to 0. Here is an example. A sinusoidal wave traveling to the positive x direction has an amplitude of 15 cm, a wavelength of 40 cm, and a frequency of 8 Hz. The vertical displacement of the medium at t is equal to 0 and x is equal to 0 is also 15 cm. You are asked to find the angular wave number, the angular frequency, period, the speed of wave, and also to determine the phase constant. Let's start with the wave number. The wave number k is found by the mathematical expression k is equal to 2 pi over lambda. 2 pi divided by 0.4 meter gives us 5 pi rad per meter. And the angular frequency omega is found with the expression omega is equal to 2 pi f. 2 pi multiplied by 8 Hz gives us 16 pi Hz, which is approximately equal to 50.24 rad per second. The period of the wave is the reciprocal of the frequency. Thus, period is equal to 1 over 8 Hz, which is equal to 0.125 seconds. The speed of the wave is then found by using the expression v is equal to omega over k. We know omega is equal to 16 pi rad per second and k is equal to 5 rad per meter, which gives us 3.2 meter per second. And finally, let's try to determine the phase constant. The mathematical expression for this traveling wave is given by y as a function of x and t is equal to 0.15 meter times sine of 5 pi rad per meter x minus 16 pi rad per second t plus 5. Substituting the value of y is equal to 15 cm at t is equal to 0 and x is equal to 0, we get 0.15 meter is equal to 0.15 meter sine phi, which gives us sine phi is equal to 1. So phi is equal to sine inverse of 1, which is equal to pi over 2. So the phase constant of this wave is 90 degrees or pi over 2. The principle of superposition. What happens if two or more waves pass through the same medium at the same time? To solve this problem of multiple waves, we use the principle of superposition. This principle is based on the vector addition of the displacement associated with each wave. The superposition principle stated that whenever two or more wave disturbances pass a particular point in medium, the resultant displacement of the point of the medium is the sum of the displacements of each individual wave disturbances. The waves do not interact. They have no effect on one another. Each wave propagates as though the other were not present. Standing wave. A standing wave is an oscillation pattern with a stationary outline that results from the superposition of two identical waves traveling in opposite directions. Nodes are defined as positions where the standing wave amplitude vanishes. They occur whenever kx in the wave expression is equal to n times p, where n stands for 1, 2, 0, 1, 2, and 3. Antinodes are points on a standing wave pattern where the standing wave amplitude is maximum, and antinodes occur whenever kx is equal to n plus half of pi. Again, n represents numbers like 0, 1, 2, and 3. The distance between adjacent nodes and antinodes is lambda over 2, and the distance between a node and an adjacent antinode is lambda over 4. The frequency at which the standing wave occurs are known as resonant frequencies of the system. The nth harmonic frequency for a stretched string and an open pipe are given by Fn is equal to Nv over 2L, where n stands for 1, 2, 3, etc. On the other hand, the nth harmonic frequency for a closed pipe is given by Fn is equal to Nv over 4L. Here, n stands for odd numbers like 1, 3, 5, etc. Sound wave. A sound wave is a longitudinal wave in an elastic medium, which could be a gas, liquid, or solid. In such a wave, the particles of the medium oscillate back and forth along the direction in which the wave travels, such that regions of high and low density are created. It is these regions of compression and rarefaction which make up the wave fronts which travels through space and carry energy. It is this region of compression and rarefaction which make up the wave fronts which travel through space and carry energy. According to their frequencies, sound waves can be divided into three categories. Audible sound. Audible sound wave ranges between 20 Hz and 20 kHz. These are generated by vibrating bodies like vocal cords, a stretched string, or membrane. Infrasonic waves are waves whose frequency lies below 20 Hz. Examples of such waves are waves produced by earthquakes, oceans, etc. Ultrasonic waves are, on the other hand, waves that have frequency greater than 20 kHz. Human ear cannot detect these waves. Certain creatures such as mosquitoes, dogs, and bats show response to these waves. A sound wave can be propagated in solid, liquid, or gas. The speed of sound in the medium depends on the density of the medium and on its elastic properties. The speed of sound in solid, for example, is given by V is equal to the square root of y over rho, where y is the Young's modulus of the solid and rho is the density of the medium. Again, the speed of sound in a fluid can also be determined using the mathematical expression V is equal to the square root of B over rho, where B stands for the bulk modulus and rho for the density of the liquid medium. The speed of sound in gas is given by V is equal to the square root of gamma times P divided by rho, where gamma is a constant called the ratio of specific heat of the gas and is equal to 1.4 for air, and P is the pressure of the gas, rho is the density. Loudness and intensity level. Loudness is audible strength of a sound wave. It's difficult to measure loudness scientifically, for it depends on the individual's hearing capacity, but it depends on the amplitude of the sound wave. Loudness is not simply sound intensity, but they are related. The larger the loudness of the sound, the greater its intensity. Intensity, on the other hand, can be defined as the rate at which energy flows through a given area per unit time. Mathematically, intensity is equal to power over area. If we take the area of a sphere, then the intensity from a sound wave can be given as P divided by 4 pi r squared. Hearing and decibel. Loudness of a sound is measured by the logarithm of intensity. The intensity I naught, which is equal to 10 to the power of minus 12 watt per meter square, is called the threshold of hearing. It is used as a reference intensity to measure the loudness of a sound. A general rule of thumb for loudness is that the power must be increased by about a factor of 10 to sound twice as loud. The intensity level of a sound in decibel is given by B is equal to 10 times the logarithm of I over I naught. The upper limit of human hearing is called threshold of pain. It's approximately 130 decibel for young people. Doppler effect. The apparent shift in the frequency of a wave due to the relative motion of the source and the observer is called Doppler effect. As the plane flies overhead, the note of the engine becomes noticeably lower, as does the siren noise from a fast-moving emergency vehicle as it passes. The effect was first noted by Christian Doppler in 1842. Let's consider a sound source moving at a speed vs and emitting a sound of frequency fs. The frequency of the sound wave reaching the observer f0, which is moving at a speed v0, is generally given by the expression f0 is equal to v plus or minus v0 divided by v minus or plus vs multiplied by fs, where v is the speed of sound. In the case when the source is moving towards a stationary observer, that is v0 is equal to 0, the frequency that reaches the observer f0 is equal to v divided by v minus vs multiplied by fs. The Doppler effect also occurs for light. When a light source approaches, there is an increase in the measured frequency, and when it recedes, then there is a decrease in frequency. Increasing frequency is called blue shift because the increase is towards the high frequency or blue end of the spectrum. Decreasing frequency is called a red shift, referring to a low frequency or red end of the color spectrum. Distant galaxies show a red shift in their light. A measurement of this shift enables astronomers to calculate their speed of recession. The following are some sample problems that appear in national university entrance exams in the preceding years. Number 1. A wave has a speed of 50 meters per second and a wavelength of 5000 meters. What is the frequency of the wave? A. 2 times 10 to the power of minus 3 Hz. B. 6 times 10 to the power of 1 Hz. C. 5 times 10 to the power of minus 2 Hz. And D. 1.8 times 10 to the power of 6 Hz. Let's solve together. We are given the speed as 50 meters per second and the frequency 25,000 meters. So you are asked to calculate the frequency of the wave. So the frequency of the wave can be calculated from the expression that frequency is equal to v over lambda. So v is 50 meters per second divided by 25,000 meters gives us 2 times 10 to the power of minus 3 Hz. So the answer is A. Number 2. An oscillating system is used to create a succession of waves on a water surface. The rate of the wave generation is 1 every 0.33 seconds. So what is the period of this wave? A. 0.3 seconds, B. 10 seconds, C. 2 seconds, and D. 3 seconds. So in this problem, we are given the frequency of the wave, which is 0.33 Hz. So you are simply required to calculate the period. And we know obviously that period is the inverse or the reciprocal of frequency. So period is equal to 1 over frequency. 1 divided by 0.33 Hz gives us 3 seconds. So the answer is D. Number 3. A transverse sinusoidal wave is traveling on a string. Which of the following statement is correct about a point on the string? A. The point moves in the same direction as the wave. B. The point moves in a simple harmonic motion with a different frequency than that of the wave. C. The point moves in a simple harmonic motion with the same angular frequency as the wave. And D. The point moves in a uniform circular motion with a different frequency than that of the wave. Let's see the alternatives one by one. A said the point moves in the same direction as the wave. This is completely false because in a transverse wave, the points move in a perpendicular direction to the wave. B. The point moves in a simple harmonic motion with a different frequency than that of the wave. This is also false because the point moves in a simple harmonic motion with the same frequency than that of the wave. So the answer is simply C, because the point moves in a simple harmonic motion with the same angular frequency as the wave. This is all we have for today. I hope you enjoyed our lesson. Till next time, goodbye everyone.